Well, hopefully it's the most important one, but it's the last one for sure. And I say that because it's important to get feedback. And number one, not only for your own design, we stream about 400 systems to our service, performance data from that. We're very interested in how multifamilies perform, but also because now we can actually have evidence in order to say this is where we're going to get into, and this is what you save in the grid, and this is how a geosystem performs. That's really the important part of it. My name is Jens Parnikau. We designed and actually installed, we're a design builder for Zero Place, and my pleasure to introduce Hugh Henderson. Became a dear friend over the years because he's a rater for NY-GEO, and we have a strong desire to make sure that the results are verified, they're correct, they're not made up, they're not modeled, they're not guessed, they're real. So that's the entire purpose here, because only then, and if you now have that confirmed by a state agency like NY-GEO, that really, we hope, brings our not only the policymakers forward, but also essentially the whole industry to say, hey, this can be a rocket ship here. We just have to prove it. So the proof is in the data. So you're next. He will walk you through the data, and then I put it a little bit in perspective of what we're doing.
Okay.
Very good.
Okay.
And I do have a laser pointer if you need one, unless you want to use that one.
So do we escape to get back to? Actually don't know how to get back. Do you know how to get back to the other presentations?
Escape.
Oh, okay. Yep. And then go to. Yep.
Oh.
Now I know what to do.
Okay, perfect.
Okay.
I don't because I'm a Mac guy, so that happens.
Okay. So yeah. So I'm gonna. So I had sort of geared this so that Jens would sort of describe the building, but I think a lot of people understand the building. It's a multifamily building with retail on the first floor. And so my job was, and I had been hired by NY-GEO to measure how the system works. And I'm a guy who kind of measures stuff. So that's kind of what I've always done, is to go into buildings and measure how they work and kind of report on the performance. And so, you know, a geothermal system is really pretty boring in that there's nothing in the basement, right? So you could see that this is a picture of the ground loops coming into the basement, and then there's a pumping station in the middle. Does that work? No. And then there's a pumping station in the middle, and up on the mezzanine in the back were two water-to-water heat pumps. Thanks, Jens. And so we wanted to, and so NY-GEO, this had been funded by the NY-GEO new construction program, this whole project. And so a lot of monitoring was already going in, and then the clean heat group at NY-GEO had funded me to add a few more meters and sensors to measure how the system works. Actually, can I borrow your pointer yet? Okay, so we already, when we came into the building, there was already monitoring of the power use on every single heat pump. You can see there was a ground loop, and then the ground loop has various heat exchangers. We added a BTU meter to measure flow and temperatures so we could know the heat rejection and extraction from the loop. And then, you know, what's novel about this system is there are water-to-water heat pumps that use the ground loop to provide water heating. And that's these units right here. We measured the power use of those. And then we also wanted to look into the details of the domestic hot water system. So we measured the energy content, flow in delta T, of the energy delivered to the building, the hot water use used by the tenants. And then we also wanted to know what was happening on the recirculation loop. So this is actually one of the first times that I've been involved in a site where we actually measured that. and measured the flow and the impacts on the recirculation loop. And we were able to learn some pretty neat things. So we started, the building was built and was occupied in 2022. It took till about mid-2022 to be fully occupied. We started data collection in early 2022, full data collection about the spring. We collected 5-minute data, and that was our main interest. We also collected 1-minute data because we were interested in some of the details about the water use, and so I'll get into some of that. And all this, like I said, was funded by the Clean Heat Group at NY-GEO to enhance the monitoring. I will point out this, obviously, so when I'm going to talk about COP, I'm going to mostly talk about the gross COP of the system, meaning the energy content of what's provided, the recirculation losses, and then I divide by the power use of the heat pump. I call that the gross COP or the plant COP, which is what you can compare to boiler efficiency, for instance. I'll also talk about the net COP, but that'll be different. It turns out energy use in this building was very good and very low. And you can see the mix. So blue is what the space heating heat pumps use, the water source heat pumps. Orange is what the domestic hot water system used. And the green that you almost can't see is the pumping power. So what was really, and of course the water heating, the water-to-water heat pumps or domestic hot water ran all year round, and they extracted heat from the loop the entire time, and we'll get into that a little more. But really what was kind of extraordinary about this compared to other systems I've ever monitored is that the pumping power was extremely low. And so the peak rate was about 18 watts per installed ton, and like normal systems are on the order of 60 watts. So I think the Clean Heat program says you have to be under 60 watts per ton. So this was quite a bit lower than that. And in best practice, usually you might use 10% of the heat pump energy for pumping. Here we were more like 3% because it was a variable speed system. Some of the overall facts is our total mechanical energy use per square foot was about 1.8 kilowatts per year per square foot. And the and then for just space heating and cooling, it was 1.4. So this was kind of a passive house or a near passive house building, and there was a passive house analysis. And so here is what the passive house tool predicted what the heating loads were going to be in 1,000 BTUs per square foot per year. The measured values are right here. Of course, we couldn't directly measure them. We only measured the energy use of the heat pump, but we used the inferred COP and the measured kilowatt hours to kind of back into what those loads were. So we basically kind of showed that the heating and cooling loads were a little higher than the passive house tool predicted, but we were pretty close. And that means the loads were just extremely low. The other thing I'll note is just like we talked about, so when your building gets very good, it turns out now heating and cooling are about the same, right? So the energy use, and this breakout I could not do perfectly because I measured heat pump energy use, and as you'll see in some of the graphs, there's a lot of mixed heating and cooling in the building. But to my best of my ability, I sort of estimate about half went to heating and half went to cooling. So why is the pumping energy so low? So like I said, 3% of what the heat pumps use. So one thing it helped, that methanol is the fluid, and methanol is pretty well known to be the lowest pumping power, the fluid with the lowest pumping power, so that helped. There were variable speed variable speed pumps. And so I like to call this sensorless control because in a traditional geothermal building, you might have, in this building and others, you have a two-way valve on every heat pump. So when the heat pump runs, the valve opens, and the heat pump turns off, it closes. And so therefore, the amount of volume, the amount of flow through the system can reduce. Normally, you might have a pressure sensor out in the system that measures the pressure across the heat pumps, and you might control that. This is, forgive me, Jens, but I call it the poor man's version of variable speed pumping. But it actually, because it doesn't have a sensor, and this is one of the first times I had measured one of these sensorless systems where it just knows the pressure across the pump, but it doesn't really know the pressure across the system. It turns out that was not much of a problem and didn't cause any problem. The other thing is this controller also has sort of a reset pressure in, just like in a VAV system with air, sometimes you might reset your pressure set point as you have lower load. You don't need the highest pressure. You only need the highest pressure at design conditions. You can probably get away with less pressure. This kind of had a reset where it could provide 100% of the pressure differential at full flow. It drops down to 50% at low flow. And this is okay. This makes certain assumptions about that the loop is half of the pressure drop and the building is the other half. Turns out it worked out pretty well. The other thing so I did a lot of geothermal variable speed pumping papers about 20 years ago. And back then, engineers loved, so the engineers loved to put valves in things like circuit setters and balancing valves and all that. All that adds pressure drop. It means your system, your delta P across the heat pumps has to be bigger to overcome all that, and kind of hurts performance. I always say, so this system did not have any of these extra components. And and engineers put these components in kind of for fear that flows might not be perfectly balanced. In reality, heat pumps are pretty tolerant to different flows, and I think there's too much emphasis put on trying to balance flows when that's not necessarily an issue. And so for this one, what Buffalo Geothermal did is they used ball valves at the heat pumps to balance, and there were some heat pumps they had to lower the flow on, but they did it all by hand, and then they removed the handle on the balancing valve. Here's ground loop temperature. So this does what every geothermal system did and what it was designed to do. So the winter temperatures were rarely below 40. The summer temperatures were rarely above 75. The loop started at about 50 degrees, the far field temperature, but then quickly fell into this annual pattern. So the first year is here, and so you can see it got back to about the same spot. Temperatures were a little higher in the second summer, but still well within what we expected and what it was designed for. So Jens would probably tell you it was designed for 30 to 90 degrees, and but when we're well within that, those bounds. Here's heat pump energy use plotted versus the daily average temperature, and each month is a different symbol. And I guess I show this graph mainly because, so here's what happened on a peak winter day, and here's what happened on a peak summer day. And then down here, like I said, this kind of mushy middle kind of is my evidence that there was a lot of mixed heating and cooling. So it didn't come down to a perfect, like sometimes buildings come down and there's a heating balance point and a cooling balance point. Here it was all muddled together. And I think that's what you would expect in multifamily, is that there's always different uses of people are doing different things in their spaces. So you see this kind of mix of behavior. So the balance point for the space heating seems to be about like it was 55 or 60 degrees. And then by the time you get to 40 degrees, the simultaneous heating cooling has gone away and you're all heating. We also see the kind of thing you normally expect in a geothermal system. Late in the summer, loop temperatures are a little hotter, so energy use is a little higher. Late in the winter, heat exchanger, the incoming temperatures are a little colder, and therefore the energy use is a little higher. But basically, this is all the things we expect to see on a geothermal loop. I like this graph because, so here's kind of a graph of the loop load. So heat extraction is positive, and heat rejection is negative. Heat extraction is positive, and you can see that we have this pretty well-defined trend with different slopes for heating and cooling. The other thing I'll point out is, the water heat pumps, which did domestic hot water heating, they extracted about that much most of the time. So you can see that the point where we crossed zero, where the load on the loop sort of hit zero and it went from positive to negative, that was about 60 or 65 degrees, but the balance point for space conditioning was lower than that. So the heat extraction had lowered our balance point on the loop in terms of load. Our peak load, so our peak winter load was about 5.7 million BTUs per day in the winter and 8 million BTUs in the summer. So still more heat rejection in the summer, but they weren't too far apart. So because I had these BTU meters on the loop, and I knew the heat extraction, heat rejection, and I know what the heat pumps use, I can sort of infer a heat pump efficiency for space conditioning. I only can do it when I'm pretty sure there's no simultaneous heating and cooling. So I looked at this, and it kind of implied that even on the coldest day, we were getting heat pump, the combined efficiency for the water heating system and the space conditioning system was about 3.6 overall. So now I'm going to focus on the domestic hot water system, because I think that's the most interesting thing that we found here. And some of this is related to, geothermal domestic water heating. Some of it is just general domestic water heating. Here's the system. Here's Jens's system. So he had 2 heat pumps, and he had 2 sets of tanks. He had a preheat stage, and he had a final stage. And what made this system work pretty well is, so in a multifamily building, you always have a recirculation return, and the question is, where should that return come? The water's coming back at 110 degrees or something like that. Should you put it back into the beginning tank, or should you put it back in the middle? And we put it in, these sets of tanks are in series. We put it into the intake on the final stage tanks, the upper, and so that left the preheat tank to be a lot colder. And so one of these heat pumps could be used on this set of tanks, and one of the heat pumps could be used on that set of tanks, and they could be swapped. And that's why you see the valves and the plumbing. And the tanks operate at different temperatures, so the COPs are different. So the water-to-water heat pump system, how did it operate? So here's a heat pump number 1 that had served the finished tank, and here's heat pump number 2. And so, of course, the one on the finished tank cycled more often. It was trying to keep the tank hot, and you can see that the final tank was, the inlet to the heat pump was typically 120, and then it would go out at 130 or 135. And then for the preheat tank, it was typically about 90. So that one had higher efficiency, and it cycled less often. So when you have a preheating tank, the heat pump serving the preheating tank has colder water, runs longer, cycles less. Where when you're trying to maintain the finished tank, you can see the cycles. And I guess, yeah, so the bottom line is that you do have these two different stages of tanks, and the heat pumps behave differently in those 2 stages. So here is kind of the COP. So the blue one is the high stage tank, or the final tank. The orange one is the preheat tank, and you can see, so the high temperature tank ran at a COP of about 3 overall across the year. The preheat tank ran at a COP of about 3.7. And of course, COPs are, for all of them, they go up in the summer because the loop is warmer. So we expect that because it's a water-to-water heat pump. The overall annual average COP for this system, yeah, this is the combined COP of the two of them. And the overall annual average that we got for this, for the combined system, was 3.3 on a gross or a plant COP basis. Water use in the, so the previous session, I don't know if you were in there, but we talked about what water use is per person and per apartment. We found that in this building, so we use 1,285 gallons a day, and the average per bedroom, and if you assume a bedroom is the same as a person, or it was about 18 gallons a day, so we saw usage right where we expected. So the other thing, and you can see here's the profile that we saw across the day. And the interesting thing, so here's the hourly profile, the square. And if I look at the instantaneous 1 minute use, we do see high fluctuations. So one thing that we found is that, so actually some of the ASHRAE guidance on peak flow rates in terms of gallons per minute kind of implies is what you use to size piping. So the incoming cold water pipe on the hot water system was a 4-inch line. And I know because I had to spend a lot of money for a flow meter to fit that line. But what we found is that 99% of the time, 99.9% of the time, the flow was below 6.2 GPM. And so that's 10 times lower than some of the ASHRAE guidance would predict. And we found this, not just here, we found this, so I've looked at 5 other multifamily buildings the last few years, and we found similar behavior. So because of diversity, and because when you put 40 apartments together, nothing ever happens at the same moment on a minute-by-minute basis, so you get this pretty big diversity. And some of this has been used, and the plumbing codes are kind of adopting or kind of listening to this information. There's some IATMO hot water sizing tools that have taken some of this new information into account. So we are kind of affecting some of the recommendations for how to size piping and things like that. The other thing, so like every hot water system, we could measure the recirculation losses. They were about 30% of the output from the heat pump. So the heat pump puts in energy comes out of the system as hot water use, and then, but 30% of the energy that comes from the heat pump goes into recirculation losses. And this is not just losses from the recirculation line, it's also disruption to the tank thermoclines and stratification and things like that. And of course, and so the recirculation line is what made the final tank so hot, because you always have 110-degree water flowing in at about 10 GPM. And so that's, and like I said, so the pipes, because of the guidance in ASHRAE and other places, the engineers expected, so a 4-inch pipe for 6 gallons a minute is a little bigger than you need. And perhaps, so we've done this on 6 sites now, and we've seen flows on this order, and maybe ASHRAE guidance is 10 times too high, maybe it's 5 times too high, but I think the thing you can conclude is that the guidance is too high, and you don't need to size for some of these trends. So here's just, here's not a surprise, city water temperatures. City main water temperatures vary a lot in the winter and the summer. It turns out when you have a city water main, it's closer to the air temperature than it is to the deep earth temperature, because the pipes are mostly at the surface, and it ranged from 45 or 40 in the winter up to 70 in the summer. And the interesting thing is, so here's the hot water supply temperature, and here's the recirculation temperature. And at some time, and so at one point, we did make some changes, and I'm going to talk about that. So we had this nice setup, this nice experimental setup, so we thought, well, let's lower the recirculation flow rate and see what happens. And so on January, the beginning of 2003, we lowered the recirculation flow rate back from the building from 9 GPM to 4 GPM. And we also, and of course, how do you choose the GPM? It's, whatever pump is cheapest at the supply store, I think is how you size it. So we've measured, so of the 6 multifamily buildings we've measured, it's always 8 to 15 GPM. And really, it only has to be high enough that the recirculation temperature coming back is 110 or 115, and that's how you can be pretty sure you have hot water to every fixture, even on the end of the line. And so one thing we did is we made this change, so we lowered the recirculation temperature, and what we saw is the delivered hot water temperature jumped up, the recirc temperature went down, not a lot, and we saw the recirculation heating losses change too. And when we looked at when we look at this period, and it turns out other things were happening in the building, but we were able to compare a few days, and so the recirculation losses were 32%. After we lowered the GPM, they became 23%. And then, and so the other thing, and then so the gross COP is the far column. That really didn't change because the heat pump is still, it's a different load, but it's still the same efficiency. But what we did see is that our net COP went down, or our COP when you just look at delivered divided by power. So when we changed our recirculation rate by from 9 to 4 GPM, we saw a 10% higher efficiency, or a 10% change in energy use. And it's not explained by the change in recirculation losses. It's also less disruption to the tank. So it's several things going on. So it shows the importance of these things that nobody pays attention to in a multifamily hot water system, kind of a big impact. So peak use. So here is a peak winter day, and it was February, and it got down to -6 early in the morning, or at 7:30 in the morning. So a little bit of a busy graph. Here's the outdoor air temperature. Here is total building power. You can't see this well, but I show the output from the solar array. I didn't talk about the fact this building has a solar array. It has 240 some odd kW of solar. And it had a big contribution to the building, but it's just, I'm going to show it didn't have much impact. So here is the point. So on that moment when it's -6, the peak demand on the water source heat pumps were 29. The DHW heat pumps weren't running at that moment. The building was 43 kW. And it turns out the building didn't peak till everybody came home later at night. So the interesting thing, so a couple of conclusions, that the building peak was not really driven by the heat pumps. So the peak on the building was because of what the occupants are doing, not because of what the heat pumps are doing. The other interesting thing is that the peak was outside the solar window, so the solar array did not change the peak demand that the building had on the utility. Similarly, here's a summer day. So and again, so here's what the heat pumps were doing. Here's what the building was doing. Here's what the solar array was doing, and you can't see it very well, but so the red is what you pull from the utility, and of course, when the sun comes out, the utility demand goes negative. But here is the peak demand that was on the water source heat pump system for space conditioning. Again, the building had a different peak. So I think the interesting thing about this is that the peak demand for this building was not driven by the HVAC system. It was driven by appliances in the apartments and what the people were doing. So I think, so the overall summary, I think heating and cooling, energy use in this building was very low, and energy use for heating and cooling were about the same. Pumping energy for this building was extraordinarily low for the reason we talked about. And I think it's, so the low-cost centralist variable speed pumping is very effective. And methanol, as well as no extra stuff in the system, no extra components. Combined COP was still 3.6 on the coldest day, even when it was -6. And of course, a cold climate air source heat pump probably would have been pretty close to 1 at that point, to state the obvious. And the other interesting thing is, so in this building, the heat pumps are not what's driving the peak demand of the building, like everyone expects, right? The expectation is building demand is driven by the HVAC system. That was not true here. And, so the solar system was big and worked well, and it provided 95% of the energy across the year, but it didn't make the building demand any different, right? The building still peaked outside. The building peak was always outside of when the array was providing energy. So the water-to-water heat pumps worked pretty well to meet the domestic hot water heating load. As Jens always, Jens was able to downsize the loop from 18 bores to 15 bores. And so he said, he always likes to say he provided the DHW system for free because the reduction in loop size offset the cost of the DHW system. The annual gross COP for the domestic hot water system was 3.3, and any air source system like a Sandin would have been more like 2 to 2.5 for comparison. In general, I think, DHW systems, and the other session, Bob Brown had talked about the fact that, plumbers need to talk to mechanical people, and mechanical people need to understand domestic hot water use, and this kind of shows that and I think some of this is happening. The codes have been have not changed for many years, and I think things are finally happening, and that excessive recirculation flows have a surprisingly large impact. And seemingly small tweaks on things nobody pays attention to can have a big impact. So that's all I have. So you want to?
Yes. So I take it as a compliment to say, hey, this is a poor man's control system. Right. I got a kick out of that one. But it proves the point. I mean, if you now have a way to, number one, make it much cheaper, but make it much better performing and long-lasting, what's wrong with that, right?
Yeah.
Yeah.
Oh, no. No, I'm Scottish, so I think the poor man's solution is always better.
I would need that pointer.
Yes.
So, okay, cool. So I want to put it a little bit in perspective. First of all, show you a little bit more details on what we had designed and what we've done. So just, again, this is about a 55,000 square foot building, and that's the apartment and common spaces. These are 46 apartments in there, only 1 and 2 bedroom apartments. They have some amenities in there, like fitness, and now they have retail spaces, a coffee shop, we were done pretty much at the end of 2022, 2023 here. And this won the first Builder of Excellent Award by NY-GEO. You see our lovely governor there, and these are kind of the owners and engineers here. And so it has a big impact because it shows you what the path forward can be. We can use lesser energy instead of more energy by electrifying a building. As a matter of fact, electricity we can use less. So again, just to emphasize here that there are a lot of innovations, what we put in there, kind of things we learned as feedback from our data monitoring for our systems, and we implement them on a continuous basis and trying to push the envelope here. So our goal was then suddenly to say, look, there's no backup here. There's no electric resistance heat. We're confident this is the most reliable way of doing it. And so there's no such thing as a supplemental electric heat element or an electric water heater as a backup for it. Everything was just 100% pure geothermal. We put 15 boreholes all underneath the building, and they are only 400 feet deep because that's where we get to the point where if we have the room, we like to make them 400 feet deep so it causes the best balance between pressure drop, pumping power, etc. And you heard that one of the art here is to pump the entire building with an average of 400 watts. I mean, this is a lot like residential circulator, which does it for this entire 60,000 square foot building. But the art is to engineer it so this is enough, and it's enough for all the heat pumps at all the times. It has a very big solar array, so all the data you said, I just want to emphasize, is without the solar here, just because we wanted to demonstrate only how much is actually done here. And even without any solar contribution, this building is the most efficient one out there and has the lowest peak per square foot ever seen in a multifamily, and it actually doesn't drive the peak in the grid anymore. So quite what we felt are some achievements here. And, but they maximized it. These are actually some of the awnings. They're all solar panels over the windows. And even the elevator shaft, I got a kick out of it there. There are 3 solar panels on top of it, just to maximize every square foot and squeeze everything in there they could get. However, the interesting part is that, obviously, this was excluded from the analysis where we said, okay, we don't know about the retail spaces, we just look at apartments and common spaces here. And everything is on a big master. They actually pay for the electricity because electricity is included in rent. Because they save so much more and have so low operating costs that it doesn't almost matter for them. But it's worth a lot for the tenants in a marketplace. How can I essentially be this attractive? We have some electricity bills of hundreds of dollars here, and the tenants pretty much don't pay anything because the owner doesn't almost pay anything. That's really the trick here. So they missed their goal of being net zero by about 2%, I believe. So this was the contribution of the solar array, and this was the overall energy grid cost for the system. But they're super happy with it and said, we should have squeezed more in there somewhere, but it's just for bragging rights. Like I said, this is really one of the better systems I've ever seen. And it's interesting that there was not very much fluctuation in terms of the overall usage of energy in this building. And this is like a dream for utility. This is a huge high load factor, and you don't have to design for the peak or do anything else really. I emphasize one big thing here. This was the average electricity used per month, about 312 kilowatt hours per month for 1 bedroom, about 420 for both bedrooms. You know what the average is of non-electrified buildings? It's about 600 kilowatt hours per apartment average in New York State. So after electrifying a building, we used less electricity than the average of an non-electrified building is on gas, for hot water, and for heating. Think about that. That means we can make this entire transition with less energy rather than more. That's if you essentially design it correctly. And just to compare, I've used this slide before. This is pretty much the data from the Department of Housing Preservation here. This is in New York City, about 1,700 houses here. Old building stock obviously uses 85 kilobtu per square foot on average in energy. This is the post-2003 building stock. These are the early adopters of passive houses. This was the Lockport Housing Authority. Because that was fully electrified, it was already very, very efficient. These are all passive house certified houses. None of them reaches actually the passive house target. This was the 50-year-old building without weatherization from the Lockport Housing Authority, where we put a GEO system in there, and that was immediately performing better than any passive house in New York City. And then this is Zero Place here. This is about twice as good, of course. This was a brand new building, passive house standard, plus the GEO system with wonderful performance. But again, my emphasis is on this, that you're looking at 1-bedroom and 2-bedroom apartments. And this is after electrification with the GEO system. This is using less electricity than a non-electrified building on average today. This is where we have to get. And nobody believes that we can. Everybody says, oh my God, we are not gonna make this transition. We can make it. We have the technology. We have working examples now. And they're real world examples. One of the things I want to emphasize here, and I did this before, this is the total energy in the peak 15 minutes at 7 o'clock in the morning, and this is the most efficient building I know. And despite that, 90% of the energy was used for heating. That's the monster. But if you now look where the energy was coming from, about 70% of that huge load was coming actually from the loop field, from the thermal battery in the ground. And that is the kicker, because the grid then only sees this up here, which also will end up as heat in the building. But this is where the efficiency comes from. It actually comes from the energy we stored in there in the summertime. And how much is that worth? Because that offsets any kind of battery capacity we need in the grid. And during the peak day, on this -6-degree morning, for the entire day, the loop field delivered 1,706 kilowatt hours. To create that as battery storage in the grid at today's battery prices, that saved $967,000. The loop field here was costing about $350,000. In other words, it paid for itself 3 times over in one day. That is what we have to remember. It is the biggest bang for the buck you can get. So this is only to emphasize that we are putting energy in there in the summertime. This is a typical summer day. We're pulling energy out of it continuously in the wintertime. It is actually this heat from the summer which is feeding all this. We're not rejecting it into the atmosphere. We're putting it underground and getting it back 6 months later. It's a perfect battery. And it just shows you here, this was the peak moment I was referring to, where 90% of the entire energy use of the building was thermal energy, and shows you how the thermal energy was fluctuating during the day. But if you now look at how much was delivered by the ground, it shows you that the ground was following that demand and automatically was giving more energy into the building when there was more needed by the heat pumps. So it's almost like a dispatchable battery. It just does it so automatically. And that's really the important part here. The other important part is, as I emphasize, we can make up all that data unless it's verified. It's verified by a state agency. And guys like you come in, and I saw that goes behind it. That really is, for me, the key aspect of this. That, if you fly to the moon, unless you take somebody along who says, yeah, this is legit, this was actually the moon, nobody will believe it. And would you have believed a couple of years ago that we can actually, through the process of electrification, use less electricity than more? It's kind of weird. It's kind of counterintuitive, isn't it? That's what we're doing here. Okay, now, let me spend the last 5 minutes before we go to questions here and showing you what happens if you don't do that. And I remember this was a headline in the Buffalo News about this summer, and saying, oh, don't electrify. Here's a bad example. Gaps in electric distribution create disruption for construction of new housing projects. That's what we fear, right? And that's what's happening all over. So some very well-meaning developer was putting 350 apartment units in here, all passive house target in Buffalo, New York, to a passive house standard. And there was a problem with that, because what happened then is they said, well, we didn't have enough capacity in the immediate area to power all those buildings. And then the article says the problem is partly about the electric capacity in the overall grid, but also about where and how the power is distributed. Is that really the problem of the grid? Or did we create that problem when we didn't put technologies in which lower that need? So as a result, panic was there. They had air source heat pumps here in, and they said it took about 6 months to study and plan and come up with a solution. National Grid said, well, we need more power there from our substations. Oh, by the way, we have to charge you $5 million extra in addition to your $30 million. That's what the developer ended up as a bill. And then he was totally surprised. He said, we would have thought we have not a power on Delaware Avenue, which is downtown Buffalo. So, and then the article concluded that the problem may only worsen with the state's push towards electrification. We maybe shouldn't do all this. The wind demand is going to be so high and will double by 2040. And the NY-GEO operators warn of this, and we shouldn't do the electrification because it puts our grid at risk and everything else. What the article didn't show, first of all, here is the load ladder for that development, and this is for each one of those 50 apartment buildings. So they're about the same size each than actually Zero Place. You might not be able to see this. This is 61,000 square foot. Zero Place was 56,000 square foot. Actually a worse climate zone than Buffalo, New York, which we, coming from Buffalo, can hardly understand and believe. But the bottom line is, the load ladder was about 1,100 kW for one of the apartments. The load application for Zero Place, thanks to GEO, was about 340 kW, 1/3 of that. And the actual consumption was about 65 kW in the winter. Less than 6% than what the load applications were for an air source heat pump driven building. Now this is design versus reality, and if you can accept, this is over designed, I get this. But where do you think I got the load ladder from for that building? I got it from because I put in a bid to do this whole building with GEO. And my bid was about $3.5 million for all 3 buildings. And it would have been $1.9 million after incentives. And the cost of the air source heat pump they actually put in was $2 million. And then the problem was that they said, nah, we're a little bit too far in the planning. I don't want to have the inconvenience of redesigning, and let's go with air source. I don't care. I don't pay for the electricity anyway. Oh boy, was that wrong. So, in conclusion, the point is, it's not the fault of the grid, or that the grid doesn't have enough energy. It is that we are not thinking about on how to reduce it and how much we can save with it. That is really the kicker here. So, in my opinion, Zero Place shows a clear path forward on how to avoid the grid collapse in the wintertime due to the increased peak demand. We've shown that now. We're not the only ones. Zach was reporting today that the air conditioning was still air conditioning dominated here in his building. The first results are coming out. We can do this, but we need GEO as a technology. We need to tap into this giant ground battery at peak times, and then we can lower the peak and essentially eliminate it. And keep in mind, it's the famous saying, where's JR? He brought this up. Whatever you get from the ground, you don't have to get from the grid. This is really what has to get into our mind, because then we can do all this transition. And we have to look at that kW, not BTUs. It's really the same kind of energy. Once we start to use electricity to heat a building. So keep that all in mind, and that's what I wanted to emphasize. Last year, Rory Christensen was here and said, hey, he compared it with a moonshot. Remember when we had a goal, we made a decision as a nation to fly to the moon, and we had no clue on how to get there. Please come in and give us solutions, help us to find a way to get there. The data we have now, which is confirmed by a state agency, tells us exactly how to get there. And it's exceeding all of our expectations. But it's also the only way I'm aware of on how to get there. Because once you electrify, you have three things. You have electric resistance heat, which will be utterly expensive, and it will collapse the grid on the worst day of the year. If you use air source heat pumps, you get pretty much in the same boat. It will save you over the year, but the worst day of the year, there simply is not much heat in the air. Plus, there's no storage component there. GEO is the only technology where you use the summer heat stored in the ground, and you get it back for free in wintertime, which avoids all the grid collapse. And that is more worth than anything else. Thank you so much for coming. We're here for questions. Thank you.
How you doing, Jason and Durant? For Zero Place, did the solar system, did you capture heat to inject that back into the ground at all for that, or?
No,
did
that
you
was
need to
only
do
a
that?
solar PV.
It was just solar PV, okay.
Data, you showed you some data to say, yes, it was there. We didn't account for any of the numbers. We just looked as if this would have not a solar system. Plus, the solar contribution was outside the envelope when the peaks were occurring. So, every day in the summertime and the wintertime, the peak was occurring at a different time than the solar system was actually contributing. So there was 0 kW coming from the solar during peak. So you need a battery. But our point is this battery is for free. You don't have to recharge it. You have it it lasts 200 years and it doesn't deplete. And we don't have to worry about the generation and the expenses in the grid and then the transmission lines to recharge that battery. It's always there. So it's ingenious in a certain way, and we never thought about this. I mean, we always knew about it, but now we have the data, and we actually see the energy flow going in and out, and you say, it avoids that one-on-one in the grid.
Yeah, I was just gonna say, or saying it another way, yeah, so the solar was there, all the numbers on building energy use, I had washed out the solar and just focusing on the building. But the solar was there, it functioned properly, it met a large portion of the load.
Yeah, but just not the peak.
Yeah, but just not the peak, that's right.
No, we did not, no.
No, it has nothing to do with the
No. That was actually, the heat was only injected in the summertime and was always extracted in the wintertime. So that was actually making the point that we have a battery there which lasts 6 months. That's the good one, or even longer. So,
Yeah, okay.
okay, any other questions?
Jens, I want to interrupt here for just a minute. I
Yeah.
did not get a chance to introduce you to, and I apologize for that. Trying to keep my car from getting towed from the parking station. Ladies and gentlemen, I'm going to just share a little bit more information about these two guys because they really are a dynamic duo. And what you saw up there today in terms of their analysis is really the key things that we have to promote in our industry. Jens has given up so much time to meet with people when we've asked him to do that, and he's met with the several of the utilities as they go through their grid planning for the future. In New York State, if you don't know, there's a whole series of meetings, revisions to their plan. The Public Service Commission has required utilities to put together a plan, and somehow the value of ground source heat pumps is not in there. And at the drop of a hat, I've asked Jens to be part of those meetings where he has gone through a version of this, and it's strange to me. I don't know if they get it yet. We may have to do that a few more times, a few more 100 times. I don't know. Jens is an international installer. You may not know that. He's done installations in Germany and the United States. He's the president of Buffalo Geothermal. He's a wonderful president for our New-York-GEO organization. And Hugh is a graduate of Cornell. He's principal of Awajina company, so he does a lot of consulting work. I don't know that much about Hugh, but I know when these two guys get together and they start talking, it's like one of those surreal moments where you just know that there's two brains working and that they're going to really provide us with the stuff we need to go forward. So I ask you to please, when this gets on the NY-GEO website, get that information, because if you can't sell that, then we're really in trouble. Am I right?
Yeah, we hope we get
That's
the point across.
We can save more just by not building out the grid through their research and stuff. So, again, I'm sorry I didn't get to do the introductions, but you're really looking at and listening to two super pros here, and I totally encourage you to take their wisdom, and it's already translated. You hardly have to translate it. It wasn't me that said whatever you get from the grid, you don't, or whatever you get from the borehole, you don't need to get to the grid. That's a true Ponicowism, so, and it's easy to remember. Any other questions? Okay, well, how about one more round of applause? Sign up for your CEUs in the back, and have a great time on your way back.
Thank you. Thanks for coming. Thanks for coming to NY-GEO.